Okay, so welcome back to this next video in which we are discussing Pavlovian, or if you like, classical conditioning. Okay, right, so in this video what I'm going to now describe to you is what is considered as Pavlovian conditioning within the Aplysia californica. Okay. However, what we will see is that if you try and compare it to the classical experiment done by Ivan Pavlov, you'll find that you run into difficulties, okay? So, what we're going to see is that it's not quite like the form of Pavlovian conditioning that we all love that's up here, okay? It's slightly different, but what you will see is the running theme is that you have the pairing of two stimuli. Okay, right, so let me now describe to you what is going to occur. Let me start by just reminding you once again what sensitization is, because I really want you to see the difference between sensitization and what I'm about to describe to you. Okay, so basically, the gill withdrawal reflex, if you take a little pipette and squirt water onto the siphon of the Aplysia californica, it causes the gill to contract. Okay? If you deliver a head shock to the Aplysia californica and wait, let's say, 2-3 minutes, and then squirt water onto the siphon of the Aplysia californica, what you see is even though you've delivered the exact same sensory stimulus, the gill contracts much more. That is sensitization of the gill withdrawal reflex by the delivery of the electric shock to the head of the Aplysia californica. What we are now going to see is what's considered Pavlovian conditioning. Basically, if you do the electric shock that you're going to deliver to the head of the Aplysia californica concurrently with squirting water onto the siphon of the Aplysia californica, then you wait 2 minutes or 3 minutes, and you do the squirting of water onto the siphon again, the contraction of the gill muscle that you get is even bigger than what you would have expected with sensitization. So you get an absolutely enormous gill contraction, okay, far bigger than if you had just shocked the head of the Aplysia californica and then waited 3 minutes and stimulated with water and seen the sensitized contraction. So there is some bigger mechanism that is going to increase the contraction of the gill if you deliver both the electric shock and the stimulation of the siphon concurrently. And because of the pairing of the two stimuli, it's considered Pavlovian conditioning. Okay, so let me now get some more paper and we'll discuss this. Okay, it's a little bit difficult to compare this to the classical Pavlovian experiment, okay? So we can have a go. Basically, we would consider the unconditioned stimulus, okay, as our electric shock. Okay, so this would be the electric shock that we deliver to the head of the Aplysia californica. Okay, we can then consider our conditional stimulus, the siphon, siphon stimulation rather, okay, with water. Okay, and when we pair these together, we can then just deliver the siphon stimulation on its own afterwards, and we would consider the conditional response, or rather the conditioned response, we would consider that the massive contraction that you get. However, it becomes more difficult to think what the unconditioned response would be, because the unconditioned response should be something that you get just in response to the electric shock. Okay, and the electric shock on its own does not cause the gill to contract. Okay, so it's more difficult then to sort of draw parallels with the original classical Pavlovian experiment. However, this response that we're going to see is best categorized as Pavlovian conditioning, although when you actually see it, it's more, to me, it seems more just like a potentiation of sensitization, but it is considered as Pavlovian conditioning, or classical conditioning. Right, so what I now want to explain to you is the neural mechanisms underlying why this occurs. Okay, so let's draw our little diagram again. So, we've got this sensory neuron here. This is the L1 sensory neuron. Okay, so here is L1. It then stimulates the L7 motor neuron, which then innervates the gill. Okay, and this is the siphon down here. We then also have the L29 neuron here, which is going to be activated by the electric shock. So, basically, what we are going to do is we're going to stimulate the siphon with water at the same time as delivering the electric shock. That means that the L29 neuron is going to fire at the same time as the L1 neuron. Okay, maybe the L29 neuron will fire a little bit later, because remember there's the pathway ahead of the L29 neuron. Okay, now this means that the L29 neuron is going to be releasing serotonin onto the axon terminal of the L1 neuron. Okay, at the same time as the L1 neuron is actually releasing neurotransmitter. So because the L1 neuron has released neurotransmitter, or rather because it's been stimulated by the water, okay, it will be in the process of releasing neurotransmitter. Now importantly, what does that mean? That means that calcium is high within the cytoplasm of the axon terminal of the L1 sensory neuron. Now, at the same time as calcium is high within the axon terminal of the L1 neuron, you are going to be releasing the serotonin from the L29 neuron onto the L1 axon terminal. Okay, and basically, when this happens, you are going to end up with the L1 neuron's capacity to release an increased amount of neurotransmitter being hugely increased. Okay, and I'll explain how in a moment. So let me just make sure that we've got this. So I'll repeat it again because it's worth repeating. So, we know that in sensitization, if you just give the electric shock without stimulating the siphon, the L29 neuron will stimulate the axon terminal of the L1 neuron to release more neurotransmitter for the foreseeable future. Okay, so whenever the L1 neuron fires an action potential now, the amount of neurotransmitter it releases onto the L7 motor neuron here is going to be increased, and therefore the L7 motor neuron will fire a greater number of action potentials. Okay, now what we're going to do is we're going to have the L1 neuron firing at the same time as the L29 neuron stimulates it with 5-hydroxytryptamine, yes. Okay, and what that will result in is the L1 neuron now releasing more neurotransmitter for the foreseeable future, and the amount of the amount by which the amount of neurotransmitter that the L1 neuron releases has increased is going to be even greater. So basically, the effect of the L29 neuron with regards to increasing the amount of neurotransmitter that the L1 neuron is going to release is going to be much greater if the L1 neuron is firing an action potential at the same time as the L29 neuron is stimulating it. Okay, so now I want to understand why. Okay, so if you didn't understand my explanation there, then hopefully if we see the molecular details, we'll understand why. So, remember, what happens is the 5-hydroxytryptamine stimulates the G protein coupled receptor, okay, which then stimulates the heterotrimeric G protein, which then goes on to stimulate the adenylyl cyclase. Now, which adenylyl cyclase did we say was specifically important? We said it was the adenylyl cyclase aplysia A. So of those 4 forms of adenylyl cyclase, the one that's particularly important in the axon terminals of the aplysia californica neurons is adenylyl cyclase aplysia A. Okay, so I'll draw this here. Right, so when you stimulate with 5-hydroxytryptamine, this is going to activate the adenylyl cyclase aplysia A, but the adenylyl cyclase aplysia A is actually also stimulated by something else, okay, and this is calcium calmodulin complexes. Okay, right, so Basically, when the calcium is higher in the axon terminal of the L1 sensory neuron, because the L1 sensory neuron has just fired an action potential and released neurotransmitter, the calcium will bind to another protein called calmodulin. Okay, so CAM is short for calmodulin. Okay, now let me just give you a little brief talk about calmodulin, at least in humans, although we think it's very similar in Aplysia californica. Okay, so basically calmodulin is this protein which has this bilobed structure. It has two lobes like so. Okay, so one of these lobes is called the N lobe, the other lobe is called the C lobe. Okay, right. And both the N lobe and the C lobe have two calcium binding sites, which means that the whole calmodulin protein has overall 4 calcium binding sites. 1, 2, 3, 4. Now, between the two lobes, you have this little linker. Okay. Now, in the structure which has not got calcium bound, which is called apocalmodulin, and the shorthand for calmodulin is uppercase C, lowercase a, uppercase n. Basically, it's hunched over in this way, okay, so the two lobes are sort of bent back towards one another, and this polypeptide that links the two lobes is a linear polypeptide, okay, so it's just amino acid after amino acid after amino acid. It's not in an alpha helical shape or anything like that. Basically, when calcium binds to these 4 calcium binding sites, 1 calcium ion in each calcium binding site, what will happen is the structure of the calmodulin changes. Okay, so basically the two lobes move further away from one another, and the linker between them goes from being a linear polypeptide to being an alpha helical structure, like so. Okay, so this is the calcium bound form, so I will put calcium ions in these dots here. Okay, so you've got calcium bound there. And this structure is now called a calcium calmodulin complex. Okay, so this is a calcium calmodulin complex. And the calcium calmodulin complex can then go on to stimulate all sorts of other proteins. Right, and one of them, in the case of the Aplysia axon terminals, is going to be adenylyl cyclase Aplysia A. Okay, so let's just recite how 5-hydroxytryptamine would usually stimulate an increased release of neurotransmitter from the axon terminal. So the 5-hydroxytryptamine would stimulate the GPCR, so this is the 5-HT receptor. This would stimulate some G protein, okay, so it would stimulate a heterotrimeric G protein, and the heterotrimeric G protein alpha subunit would then go off and stimulate the adenylyl cyclase Aplysia A. The adenylyl cyclase Aplysia A within the axon terminal is going to convert ATP to cyclic AMP and pyrophosphate, okay, so PPI, and then the cyclic AMP is going to go off and activate protein kinase A. We've then discussed that protein kinase A is going to phosphorylate and cause the shutting of this special serotonin-sensitive potassium channel here, this S channel, okay? And basically, when the S channel closes, that's going to prolong the action potential, okay? Because you've now got less potassium coming in the repolarizing phase of the action potential. And also, when you prolong the action potential, the result of that for the release of neurotransmitter is that the voltage-gated calcium channels in the axon terminal are going to stay open for longer, because when the action potential is longer, the time for which you are beyond the threshold potential for these voltage-gated calcium channels is going to be greater. Okay, more voltage-gated calcium channel open time, more calcium coming in. Okay, more calcium coming in, more neurotransmitter release. Now, basically, if you have more phosphorylation of these S channels, then you're going to get more S channels shutting, and the prolonging of the action potential is going to be greater and greater and greater. The more S channels which you phosphorylate, the greater is the prolonging of the action potential, the greater is the amount of calcium that will come in, and the greater is the increase in the release of neurotransmitter that you will see. So, it's all about how much you stimulate protein kinase A, and this is the basic answer to how giving these two stimuli, the water stimulation of the siphon and the electric shock, together are going to give you an increased amount of neurotransmitter released from this L1 sensory neuron, even compared to the amount that you'd see if you just delivered the head shock, i.e. if you'd had sensitization. Basically, if you deliver both stimuli together, then the serotonin is going to do this. But also, the calcium is already going to be present in the axon terminal because the L1 sensory neuron has been stimulated by the water that you've applied to the siphon. This calcium will bind to calmodulin to create calcium-calmodulin complexes, and then the calcium-calmodulin complexes bind to the C1b domain, or the equivalent of the C1b domain, because the C1b domain is the name for it in human adenylyl cyclases, but an equivalent domain to that in adenylyl cyclase aplasia A, and basically calcium-calmodulin complexes binding there also facilitates the dimerization of the C1a and the C1b and the C2a domain, shown here in orange, to produce the active adenylyl cyclase. And the addition of both of these stimuli together, the G protein stimulating the adenylyl cyclase aplasia A and the calcium-calmodulin complexes stimulating the adenylyl cyclase aplasia A, are synergistic. Now, what does that mean? Okay, so basically synergistic means that if they work together, the amount of stimulation they produce is more than just the added stimulation of both of them. So let me explain that. So if we draw a little graph, because that's probably the best way to do this. Okay, if we have adenylyl cyclase aplasia A activity on the y-axis, so this is how active this enzyme is basically. Okay, then if we look at stimulating just with serotonin, okay, so just with the G protein that's coupled to the serotonin receptor, we might get an answer like this. If we look at just calcium-calmodulin complexes, okay, we might get some answer like this. Basically, if you put both of them together, the answer that you get is more than just this one plus this one. It might be something right up here. So if I just added these two together, I might get something like that. But when you apply them both together, you get something far bigger than just the responses from the two alone added together. That is the concept of synergism. If two things work synergistically, it means that the stimulation that they produce when they are both applied together is going to be far more than just the stimulation that the two produce on their own added together. So you don't just take this and add them together to get the answer. That's wrong. You get something far bigger. Okay, and if that is the case, that's called synergism. Okay, so basically, together the G protein and the calcium-calmodulin complexes will hugely activate the adenylyl cyclase aplasia A, and that will result in a huge production of cyclic AMP, a huge activation of protein kinase A, and a huge phosphorylation of the S channels, these serotonin-sensitive potassium channels. Therefore, you'll get loads of the S channels shutting, and therefore you will get huge prolonging of the action potential, and therefore the voltage-gated calcium channels will stay open for longer every time this L1 sensory neuron fires in the near future, and therefore you'll release a huge amount of more neurotransmitter every time the L1 sensory neuron is activated. And that is why you get this massive gill contraction every time you stimulate the siphon after doing this. And this sort of potentiated version of sensitization is called Pavlovian conditioning because of the need for the association of the two stimuli. You need to give the electric shock and the siphon stimulation at the same time if you want to see this response. Okay, so that then now concludes my discussion of Pavlovian conditioning.